Imagine a robot exploring an unknown environment, moving through spaces without any external positioning systems like GPS. How does it know where it is, or more precisely, how much it has moved? This is a fundamental challenge in robotics, crucial for everything from autonomous vehicles to robotic explorers on distant planets. Visual odometry, or VO, estimates a robot's pose, meaning its position and orientation, by analyzing a sequence of images captured by its onboard cameras. It works by detecting and tracking distinct visual features across these consecutive frames, without relying on any prior map or external reference points. Essentially, it determines how the camera itself has moved relative to the scene. The core mechanism behind VO involves several steps. First, it identifies stable and unique points or features in the current camera image. These could be corners, edges, or texture patterns. Next, it tracks these features in the subsequent image, identifying which points correspond to which. By observing the apparent two-dimensional motion of these features across the camera's image plane and applying principles of projective geometry, VO can mathematically deduce the camera's three-dimensional motion. This process often leverages epipolar geometry, which describes the geometric relationship between two images of the same scene from different viewpoints. For practical application, this means a robot can continuously update its estimated position and orientation in real time as it moves through its environment. It is a relative pose estimate, not an absolute one, meaning it calculates movement from the previous position, rather than providing a global coordinate. This capability is vital for autonomous navigation, allowing robots to understand their immediate surroundings and plan paths without needing pre-built maps. Think of it as the robot looking at its feet to see where it has just stepped, constantly updating its internal sense of movement. A fascinating aspect of VO is its inherent scale ambiguity when using a single monocular camera. Without a second camera or a known object size, the system can only determine movement up to an unknown scale factor. This is why stereo camera setups or integration with an inertial measurement unit, or IMU, are common for providing scale. It is also important to understand the concept of drift, which is the accumulation of small errors over time. Since each pose estimate is based on the previous one, any tiny inaccuracies compound, causing the estimated path to gradually diverge from the true path. Ultimately, visual odometry provides robots with an incredibly powerful and self-contained way to perceive their own motion. It is a fundamental building block for advanced autonomous systems, offering robust, real-time relative localization that forms the basis for tasks like path planning, obstacle avoidance, and even constructing detailed three-dimensional maps of the world, making it an indispensable tool in the robotics toolkit.
If you love robotics, like, subscribe, and keep building with us.